Imagine you're looking at a massive galaxy through a powerful telescope. Millions of stars swirling in a graceful spiral, like a cosmic pinwheel. Based on known laws of physics, scientists would expect to find the stars near the center spinning the fastest, and the ones on the edges moving more slowly, just like planets in our solar system. But in the 1970s, astronomer Vera Rubin made a shocking discovery. When she measured how fast stars were moving at different points in galaxies, she found that the stars on the edges were moving just as fast as the ones near the center. That shouldn't be possible. There simply wasn't enough visible mass in the known stars, gas, and dust of the universe to generate the gravity needed to explain this observation and hold those fast-moving stars in place. So why don't galaxies fly apart? Scientists also noticed that entire galaxy clusters were holding together more tightly than expected, and that gravitational lensing from distant galaxies is too strong, meaning light from these galaxies bent too much as it passed near massive objects, more than visible matter could explain. All of these mysteries pointed to the same thing. Something else must be out there, something that's invisible, but has mass, providing this extra gravity. But what? That question opened the door to one of the greatest puzzles in modern science, one we're still trying to solve today. In this lesson, we'll explore the invisible stuff that holds the universe together: dark matter. So what exactly is dark matter? Well, we're not totally sure yet, and that's what makes it so fascinating. We call it dark because it doesn't emit, reflect, or absorb light. It's completely invisible to telescopes. It doesn't glow, it doesn't even block light like a planet or a dust cloud might. It's transparent to light, to X-rays, to just about everything we use to detect normal matter. But it does have mass, and mass means gravity. We know dark matter exists because of the way it exerts a force on things. Think about the wind. We can't actually see the air particles moving, but how do we know that wind exists? Pause the video for a moment and brainstorm some thoughts. You can't see the wind, but you can see it shake the trees. In the same way, dark matter warps the space around stars, galaxies, and even affects light itself. Here's what we do know about dark matter so far. It makes up about 85% of the total matter in the universe. It doesn't interact with normal matter in the usual ways. It doesn't collide, stick, or clump like atoms do. It seems to pass right through stars, planets, and even us without leaving a trace. It holds galaxies and galaxy clusters together, acting like invisible glue. And it helps shape the large-scale structure of the universe. But if dark matter doesn't emit light or bump into things like regular matter, what could it be made of? One possibility is that it's made of new types of particles we haven't discovered yet. Scientists have proposed candidates like WIMPs, short for weakly interacting massive particles. These hypothetical particles would have mass and gravity but barely interact with normal matter. Another possibility is axions, extremely light particles that could exist in huge numbers. Though perhaps your most burning question right now isn't so much about the physical mechanics of dark matter, but instead a more practical one. If we have no way of seeing or detecting it, how in the world do scientists study it? Well, it's a topic that's currently a hotbed of scientific research, in no small part due to the challenge of finding it. After all, who wouldn't want to be the astronomer that finally solves the biggest cosmological mystery of our generation? Let's take a look at how they're going about it. Studying something we can't see, like dark matter, isn't easy. Because dark matter doesn't give off light or energy, scientists have to look for it in creative ways. At research facilities, such as at Fermilab in Illinois, experiments to find dark matter are conducted deep underground. Being underground helps protect the detectors from everyday cosmic rays and radiation, which could drown out the tiny signals scientists are hoping to detect. These labs use super sensitive instruments to try to spot the rare moment when a dark matter particle might bump into normal matter. So far, no confirmed interactions have been seen, but the search is still very much alive. Astronomers also use giant telescopes to look for signs of dark matter through gravitational lensing. When light from a distant galaxy bends more than expected as it passes near a massive object, that extra bending might be caused by dark matter, mass that we can't see, but that still affects the light. One of the strongest pieces of evidence for dark matter comes from an event called the bullet cluster, a massive collision between two galaxy clusters. When scientists observed the collision, they saw that most of the visible matter, like hot gas, had slammed together in the center, just like you'd expect in a giant crash. But then they used gravitational lensing to figure out where the majority of the mass really was. What they found was surprising. Most of the mass wasn't in the center where the gas had piled up. Instead, it was found around the galaxies themselves, on the outer edges, almost like something invisible had passed right through the collision without getting slowed down. That invisible something? Most likely, dark matter. Around the world, scientists are teaming up to solve the dark matter puzzle. New telescopes, like the Vera Rubin Observatory in Chile, will scan the sky for years, tracking billions of galaxies to map where dark matter might be. Space telescope missions, like Euclid, launched by the European Space Agency, are aiming to map the invisible structure of the universe itself, helping us locate more dark matter. Scientists are also using powerful particle accelerators, like the Large Hadron Collider, in an attempt to create dark matter particles through collisions. While these particles wouldn't be seen directly, their presence could be revealed through missing energy in high-speed collisions, offering another chance to glimpse the invisible. It's strange to think that the stuff we can see, stars, planets, and everything on Earth, is only a tiny fraction of what's actually out there. The rest, the dark matter, is all around us, shaping the universe, but completely hidden. So no, we don't know exactly what dark matter is yet. But by studying what it does, scientists are getting closer. And every clue brings us one step nearer to understanding the invisible backbone of the cosmos. In our last lesson, we saw how galaxies formed from tiny fluctuations in gas during the early universe. But there was a problem. Those galaxies formed too quickly and spun too fast to be held together by visible matter alone. So scientists started asking, what if there's more mass out there than we can see? That's where dark matter comes in. Though invisible, it has mass. And anything with mass creates a gravitational field. If dark matter surrounds galaxies like a giant invisible halo, it could explain why stars near the edges move faster than expected. It's the missing mass that's been holding galaxies and entire clusters together. Dark matter is what allowed the structure of the universe to form so quickly after the Big Bang. Its gravity would have started drawing matter together long before light could travel freely, speeding up the process of galaxy formation. When scientists run computer simulations of the early universe, the models that include dark matter create a universe that looks much more like our own than the models that leave it out. We still haven't seen a dark matter particle directly, but the way it shapes galaxies, bends light, and fits into our models of the cosmos gives us strong confidence that it's real. That said, science always strives to keep an open mind. Some researchers are exploring alternative ideas, like the possibility that gravity works differently on very large scales. These theories, known as modified gravity, try to explain the same observations without needing dark matter. But so far, none have matched the data as well as the dark matter model. So while we don't yet know what dark matter is, we're pretty sure it's there. It fills in the gaps, connects the dots, and helps us make sense of the universe's evolution, from a hot, dense beginning to a vast web of galaxies stretching across space. But guess what? This mystery isn't even close to being a closed case, because dark matter has an equally mysterious cousin, dark energy. Just as dark matter helps explain why the universe holds together, scientists have uncovered another equally puzzling force, dark energy. Instead of drawing things together, it seems to be pushing the universe apart faster and faster. While dark matter acts like gravity's secret helper, holding the universe together, dark energy feels like its nemesis, working against gravity to drive more expansion of the universe. What is dark energy? That's still a mystery, but like dark matter, it's shaping the universe in ways we're only beginning to understand. In your lesson activities, you'll take a deeper dive into dark energy and find yourself at the forefront of scientific discovery. But that's it for today, Cosmic Explorers. Until next time, keep marveling at all the wonders of our universe.
Hey, hey.